In this example, we have two loudspeakers separated by 2 meters as shown here. You'll notice I've got my diagram duplicated. That's just so that I can have two diagrams for doing some workings. The speakers are emitting a tone of 700 hertz, and those speakers are in phase. A listener stands 5 centimeters in front of the loudspeakers, so that's our horizontal distance here, and he's 2 meters to one side of center, so he's 2 meters this way. We might notice at this point that there's 2 meters between the speakers, so it's 1 meter from the center line to the top speaker and 1 meter from the center line to the bottom speaker. The speed of sound in the room is 341 meters per second. Does the person hear loud sound or no sound, or is it constructive or destructive interference? So what we'll do is we'll just have a look at our conditions for interference. We know that path length is important, so we'll calculate delta D. We know wavelength is important, so we'll calculate lambda. And then we'll compare what we find to our conditions for interference and see if that matches loud or quiet or constructive or destructive. So let's label our speakers 1 and 2. I'm going to label my bottom speaker number 2, and I'll label my top speaker number 1. Let's go ahead and find D1 first. So D1 is the distance from my person to speaker 1. That line is already drawn. So what do I know about this? I know that the person is 5 meters horizontally from the speaker, 5 meters. And then the distances I know is that he's 2 meters vertically from the speaker. So this is 2 meters. Then I also know that the speaker is 1 meter from the center. That means this side of my triangle is 1 meter, 2 meters minus 1 meter. Okay, if I want to calculate D1, I'll just use Pythagorean theorem. D1 is the square root of 5 meters squared plus 1 meters squared equals the square root of 26 in meters. You can write that as a number if you wish. I think I'll just leave it as root 21 for now. Okay, I'd also like to find the distance D2. So D2 is from speaker 2 to my person. There's D2. The person is 5 meters horizontally. And then here's our vertical distance. We know that the person is 2 meters from the center, and we know that the bottom speaker is 1 meter from the center. So our person is 3 meters from the bottom speaker. So D2 we'll find in the same method as we found D1, 5 meters squared plus 3 meters squared. Take the square root, gives us the square root of 34 meters. Again, you can put that in as a number if you wish. I'll just go with root 34. Now our first step is let's find the path difference. Delta D is D2 minus D1 equals root 34 meters minus root 26 meters. You can drop the absolute value signs or leave them in, doesn't matter, because root 34 minus root 26 is going to be positive. And when we calculate delta D, that gives us 0.732 meters. Okay, we have delta D, next find lambda, then we'll compare. So we've got our delta D, next step is find lambda. We know V equals F lambda. That means lambda equals V over F. We're given our V is 341 meters per second. Divided by our frequency, that's given us 700 hertz. So our wavelength then is equal to 0.487 meters. Okay, next step is let's compare. So we know that our relationship between delta D and lambda is important. Let's find that relationship. Delta D divided by lambda is 0.732 meters divided by 0.487 meters, and that's equal to 1.5. So our relationship between delta D and lambda is that delta D is 1.50 times lambda. Okay, which condition does this match? First off, we're told that the speakers are emitting tone in phase. So we're looking at sound sources in phase. And let's highlight those equations. Which equation is the correct one? Well, if delta D is an integer multiple of the wavelength, that's constructive. If it's a half integer multiple, then that's destructive. So our condition matches delta D equals n lambda over 2, where n equals 3, and that condition is destructive or quiet sound. And then for the last part of the question, how would this change if the speakers emitted sound out of phase? Well, if the speakers emitted sound out of phase, then all of a sudden our condition of delta D equals 1.5 lambda, that would match constructive interference. So if we swapped our speaker wires and made them emit sound out of phase, all of a sudden we would hear loud sound. For this example now, we have two loudspeakers, and we'll draw as we go. They're separated by 5 meters, and they emit a 732 hertz tone out of phase. So we'll write out of phase, F equals 732 hertz. A listener stands 10 meters in front of one of the loudspeakers. The room temperature is 25 degrees Celsius. And we want to know what is the path difference where the person is, what does the person hear, and what happens when the person walks towards the speaker in front of her. So let's start by seeing what we can figure out right off the bat. They're out of phase, so we know that's telling us about the conditions of interference. If the frequency is 732 hertz, we can find the wavelength from doing speed of sound divided by frequency. Speed of sound we're going to have to calculate from the temperature. We know the equation for speed of sound is 331 meters per second times the square root of the temperature in degrees Celsius plus 273, all divided by 273 and take the square root. Okay, when we run that through the calculator, we should get 345.8 meters per second. So if the room is warm, the speed of sound is a little higher. So we do 345.8, divide that by 732, and we get a wavelength of 0.472 meters. The problem didn't really ask us for any of that at the beginning, but now we have a nice complete list of all the things we know. Our problem originally asks us to find the path difference, delta D. We know that's D2 minus D1. So we're going to have to sort out D2 and D1. I'll start by labeling my speakers, 1 and 2. D1 is the distance between the person and speaker 1. So D1 is easy. D1 is 10 meters. D2 is the distance between the person and speaker 2. We notice that D2 is the hypotenuse of a right angle triangle where the legs are 10 meters and 5 meters. So D2 is the square root of 10 meters squared plus 5 meters squared. So D2 is equal to 11.18 meters. All right, when we find our path difference delta D, we do 11.18 meters, subtract 10 meters, and we get 1.18 meters for our path difference. I recommend in these path difference problems, you often work in 4 or 5 significant digits. That's because if D1 and D2 are a little bit close, you might round yourself out of some figs, sig figs, and delta D. All right, so the first part of the question, what is the path difference? Our answer to that is 1.18 meters. All right, that question's done. Does the person hear a loud sound or no sound? So we're going to have to compare our path difference with our wavelength. So let's just write down our path difference again. Delta D equals 1.18 meters. Let's write down our wavelength again. Lambda was 0.472 meters. Let's compare our path difference and our wavelength. Delta D over lambda is 1.18 meters divided by 0.472 meters. And that gives us delta D over lambda, let me grab my calculator, 2.5. That means delta D equals 2.50 lambda. We remember that our sources are out of phase, so we're looking at the out of phase sources. And we're asking what condition of interference do we have? Well, we have delta D equals a half integer multiple of lambda. So we must have constructive or loud interference. So we see it matches delta D equals n lambda over 2 with n equals 5. Therefore, it's constructive interference and the person hears loud sound. Okay, so that's this part of the question done. Last part might get a little bit trickier. The person walks toward the speaker in front of her. How far has she moved when she hears a loud sound or the next loud sound? So let's just jot down that diagram again. So we've got 5 meters between the speakers. The person was originally at 10 meters, but now walks inward a little bit. So now our person is right here. We don't know where she's standing now. That distance is something. So the person was originally at 10 meters, and now she's in a little bit closer. So how far has she moved when she hears a loud sound? So we have to use our conditions for interference again. We know we're talking about constructive interference. So next loud sound means constructive. So delta D equals n lambda over 2. We have to know what to put in for n. When our person was out at 10 meters, our n value was equal to 5. When our person moves in closer, our n value gets bigger. So n has to go to 7 because it's all the odd integers. If you don't quite remember where that came from, go back to one of our problems about Susie in this lecture, and that should explain why n gets bigger. It's because the path difference gets bigger. Okay, so delta D is going to be n lambda over 2, so 7 times lambda over 2. If you're a numbers kind of person, you can pop in 0.742 and solve for a number. I think I'll just leave it at this for the moment. So we also have to put in what is delta D. Delta D is D2 minus D1. Let's see what we have for D2 and D1. So D1 is between the person and speaker 1. D1 is equal to X. D2 is the person to speaker 2. That's the hypotenuse of a right-angled triangle where the two legs are X and 5. So D2 is the square root of X squared plus 5 meters squared. I'm just going to sacrifice units and significant figures here just for simplicity. So when I find my path difference, delta D, it's the square root of X squared plus 5 squared, which is 25, subtract X. I've dropped my absolute value signs because I know this is a positive value. Okay, now I have to put these two expressions together and solve for X. I'll do that on the next slide. Okay, let's put together our two expressions for delta D. So this term is going to equal this term because they're both descriptions of delta D. Square root of X squared plus 25 subtract X equals 7 lambda over 2. The only unknown here is X, so we want to solve for X. I'll start by taking X over to this side. Next, what I'm going to do is square both sides. So the square of a square root just gives us the argument. Then I have to square 7 lambda over 2, 49 lambda over 4. I have to square X. And then it'll be 2 times X times 7 lambda over 2. So it'll be plus 2 times X times 7 lambda over 2. Those two cancel, and I've got 7 times lambda times X. You'll see that we've got X squared on both sides, so they cancel. Now I want to solve for X. So X times 7 lambda equals 49 lambda over 4 minus 25. Divide both sides by 7 lambda. and I can solve for my x value. So x is 49 times lambda. Lambda was 0.472 meters. That's divided by 4, subtract 25, then divide the whole thing by 7 times lambda. And what we get when we do that in the calculator is 5.82 meters. So her new position is 5.82 meters. So the new value of x, 5.82 meters. How far she moved is what the problem asked for. How far moved would be, well, she started at 10 and moved into 5.82. Let's call that delta x. That would be 10 minus 5.82, and that would be 4.18 meters. So she had to move 4.18 meters to get to the next loud sound. That clues us up for our sound and wave section of the course. Next, we'll be getting started on electric charges, electric fields, and electric forces.